Hey, Assalamualaikum and good day everyone. We will continue our lecture with lag controller. Okay, let's learn about the lag controller using this example. We have the following plan: GP equals to 1 over S plus 1, S plus 5. Let's say we want to improve the system response that give TP less than 1 second, the steady state error less than 5% for a step input, while keeping the percent overshoot less than 10%. So the design procedures for the PI controllers or the lag controllers as follows. We have our GC equals to KC S plus A over S plus B. So you could remember that for the PI controller, actually we have our GC for PI is equals to KC S plus A over S here. Alright, but actually for this one, for the lag controller, we have another term here, which is S plus B here, right? We have S plus B. So in this case, we have the B value is actually greater than 0 and less than A. To approximate the function of PI, we set 0 to a small value, which is in this case we select B equals to 0.1. Why we want to select the small value? Because we want to the pole which is here is actually S at 0 here, S at origin. So that's why we select B equals to 0.1. And for PI we select A equals to 1. This one is because we want to cancel out with the smallest pole of the plant here, right? And we can plot it, since we know that we have S plus 1 and then we have S plus 0.1. We can plot the root locus, the loop transfer function here, and we will find that at the root locus, the breakaway point is at negative 2.55. Okay, so we have learned in previous examples to get TP less than 1 second, we will select the omega D equals to 3. Okay, so we will have our point of closed loop poles which are located at S equals to negative 2.55 plus J3. And then we can calculate the value of Kc. So we have here Kc equals to S plus 0.1 and S plus 5. And then actually we have over 1 here. Okay, so for the location of closed loop poles at negative 2.55 plus J3, and then we will get the value is equals to 15. Okay, let's look at the example using Matlab. Okay, for this one, for the lag controller, this is our let me see. Okay, this is our GP here. This is GP is equals to 1 over S plus 1, S plus 5. So we have known that our S is equals to negative 2.55 plus 3i, A equals to 1, and B equals to 0.1. So actually for this one, how do I get negative 2.55 here? Is actually we can get from our, okay, for this one we have our G. Okay, so now we select our initial GC is equals to A and B value that we have described, and then our init GC here. So this is our G, resultant of a GP multiplied with initial GC. So we can plot the R locus of G. So what we get here is this one, and okay, So here, that's why we get the breakaway point here is negative 2.55 here. Okay, that's why we have our S equals to negative 2.55 plus 3i3, because we want the TP less than 1 second. Okay, and then we can calculate the value of Kc using this formula here. And then we can plot the GC. Okay, so this is our Kc, which is equals to 15. And then we can use the Kc to have our GC here. So our GC is equals to 15 S plus 1 over S plus 0.1. So we can show that we have here in the lecture notes. And then here we already know that GC, then we can calculate the KP. So in this case, we know that it's a step input, so that's why we find KP. So limit S approaching 0 of this is our G here. Okay, this is our G, which is equals to is actually GP multiplied by GC. So we get 15 over S plus 0.1, S plus 5, which is equals to 0. And then we can find next the steady state error here, 1 over 1 plus Kp, which is equals to about 3%. So we have obtained 3%, which is less than 5% requirements. Okay, let's use the Matlab. Okay, to find the Kp and steady state error, I define capital S here because I don't want to miss with the S here that we use to define the location of closed loop poles. So again, I use the mean real function to cancel out S plus 1 here with the pole of the plant. And then I define the GS here, and then I can find the limit of GS here, which is S approaching 0, and then I will get the steady state error. Here I use sim to poly because in this case, when we run this one, our Kp is equals to 30, but here our Kp is actually a symbolic. It's a symbolic. So we need to convert it to numbers. So that's why here I use a sim to poly function to convert it to. So our ESS here is in numbers. Okay, so it is 0.323, which is 3.2%. Okay, and then we can plot the using the CISO tool here, and what we get here is actually we have this plot here, and then the step response for this one is about 6.92% at 1.05 seconds. So we could actually increase or improve this. So we want to have the percent overshoot which less than 10% here. We can increase the C value. Let's say we increase to 17. So we increase to 17. What happened is we have the overshoot is 8.93. Maybe we can increase to 18. So the overshoot here is about 9.9%. So it's very much close to 10%. So you can see here the overshoot is 9.9%, which is less than 10%, at time 0.9 seconds, which is less than the requirements, which is 1 second. So we actually have successfully obtained all the 3 requirements for the design, which is percentage overshoot less than 10%, at time equals or less than 1 second, and the steady state error we get is 3%, which is less than 5% per design requirements. Okay, so you can refer to the lecture notes here, and then what we have here, and Yeah, it's actually pretty much the same for the lecture notes as a result we get from our simulation in Matlab. Okay, that's it for this lag controller design. I will explain in the next video about the lead lag controller. Until then, thank you very much. Assalamualaikum and bye bye.